Actually, on your Smith chart, there are two different coordinates overlap each other. Two coordinates. One of that is about your reflection coefficient at the input end. Okay, this is the same picture. If your length of transmission line is getting longer and longer according to your definition, theta equals to minus 2 beta L, you are changing the position on your gamma plane. Okay? Understand? And then it's your theta, changing the position. So where it is, where your angle is, the radius and the angle means your value of reflection coefficient. Okay? Also, there is another picture we just derived here. There is a set of circles which comes from the real part of the input impedance normalized by the characteristic impedance. There are two circles. Okay? The position, if your position is on the circle of R, L equals 1. It is on the circle of, I write down there are differences. So A, when A equals to different situation, you will have the real part of the normalized input impedance according to changing with different circle, the position of the circle. Okay? So the first one, I do it again. Okay. Actually, this circle is overlap each other. It's your Smith chart. You can see reflection coefficient, which is a complex value with the absolute value and the phase. Also, you can see your input impedance, which is normalized. Okay? So, for this circle, if A equals to 0, then it is, if your input impedance has no real number, it is outside the circle. Okay, it's the outer circle. Okay. And if it is infinite, it is only one point. One thing is interesting. So what is this exactly? Is this infinite or 0? They are the same. On this position means it is infinite, and also it is 0 for your real part. Why? Okay, let's think about it later, okay? But for the third one, it's easier. For this circle means your real part of input impedance is the same as your characteristic impedance. It is 1, right? Because they are the same, so 1. The ratio is the same, so it means that's the same. Okay, so this And according to the relationship I explained, we will have a lot of the circle. Every circle, your right edge of the circle is at the point x equal 1, y equal 0. They all accumulate here. Okay? So this is the for only this part. And the same, we do totally the same technique, and you can check the website for the rest of the imaginary part. For this part, for this imaginary part, you can change to this function. It's more complex function, right? So what is this function? Let's look at this function. So for the imaginary part. For the case, if b equals to 0, for the case b equals to 0, what's that? Sorry, I have to walk. If b equals to 0, the equation is x minus 1 if b equals to 0, it is x minus 1 squared plus y minus infinite square equals to infinite. So weird. So what is this exactly? I think I didn't make a mistake. But what is that? X, Y, right? I shift the center to also 1, 0. This is my center, right? And where is the location of my center is very far away from here. But I believe that x, the position x of the center is at 1, but the y is very high, okay? And for the radius is infinite. So the first equation you obtain that, because if the radius is very large and the position, the center of the y is very large, so it's like a huge circle, right? So this line means y equals 0. Now we are talking about this is B, right? This is the B we talk about. The imaginary part, function of B. If XL is 0, if there is no imaginary part, it's this line, the center of your Smith chart, if XL is 0, okay? How about when B equals to infinite? So if B is infinite, our equation change to x minus 1 square plus y square equals to 0, which is this point again, right? 0 and infinite meet again for imaginary part. Okay? And you can also try b equals to 1 and b equals to minus 1. Let's try b equals to 1, okay? If b equals to 1, what's that? If b equals to 1, you can obtain your equation becomes right? So it is a circle, center is here, the radius is 1, right? So you will have and the minus 1, the location of y become plus 1. The location of the circle will go down from here. This is minus 1. For this imaginary circle, they always have the relationship that I shift, no matter if I shift, I always shift to 1 over y, and the radius is always 1 over y. How much I shift it, and the radius is the same. So, understand? Then you can find out the imaginary part of the circle. So all the circle, they also, for the upper circle, all the edge of the bottom circle is connected to here. All the bottom circle, all the top of the edge is connected to 1 and 0. And you can see actually there are two parts of the circle, which is B is positive and the B is negative. For the positive, they will have a lot of circle here. Okay, and then for the negative, you have a lot of circle here. So this can become your symmetry. Okay? I explain very clear. I expand much more than your textbook. Much more than your textbook. All the details about Smith chart, and I use the notation only A, B, X, Y is easy to understand, right? If I use the original gamma I, gamma R, Z, RL, XL, maybe you get this. Just change to X, Y, A, B. It's very easy to understand. Okay, so what can we do by using Smith chart? There are many examples. Actually, all the phenomena on this figure can be illustrated by your Smith chart. If you change the length of the line, it's like you just change the position. You use the clockwise circle on the position. You can see the reflection coefficient is keeping the same, right? But your input impedance can be determined, can be seen by the real number circle and the imaginary number circle. Okay. You can see the impedance is changing. For one of the example we tried before is one of the very typical example is here. When it is short, at L equals to 0, and I change in the length of the transmission line will become open and short, and open and short, and open and short, right? Remember this picture? So on the Smith chart, it is short, open, short, open, short. It's on the circle of the outer, on the outer circle. This is talking about the first and the second example in here. 0, infinite, 0, infinite, 0, infinite of the input impedance. Okay, so the outside circle, it is open and short. Okay, and you can see for the half wavelength, one circle is the pi over 2. It's a half wavelength. So every time the transmission line has lambda over 2, they will come back to your beginning. Okay? And every time you are going to use a quarter wavelength transmission line. You from here go to here, or from here come to here. You can see the number on your Smith chart. You can making a quarter wave transmission line, and you will see that. Do you remember the relationship about the quarter wave transmission line? We usually use a transmission line if it is lambda over 4. Your Z in, and this is Z0, ZL, and you have a relationship like Z0 squared equals to Z in multiplied ZL. Or maybe you will say Z0 equals to the square root of Z in ZL. Remember this one? Right? So you can find out, like, for example, if you find out it is 2, if this pi is 2, and this pi is 0.5. So this is the same. On your Smith chart, you can see they always multiply to each other will be the same. This is the meaning of quarter wave transmission line. Okay? And also, one of the very important things is something on the center, which means your imaginary part is 0. Your real part is the same as your Z0, right? which means your ZL equals to Z0. So at the center here is matched. We always go back to matched. We want Z0, and here is Z0, only this point. What is the good for this point? Because the radius of this point, if the green line, green is when you have a length of the transmission line, right? You increase the length, they will have a circle. But what if your radius is 0 or very close to 0? It's around your center. No matter how long your length is, they are always matched. So at this point it is matched. Okay. Question? Question? Okay. And we will have an exercise at the end. Okay, one more thing. The equation I directly derived from our input impedance. Do you remember this one? When you divide Z in to Z0, you can compare with the circle. The equation of our circle is very similar to the original equation. They are very similar because theta is defined as -2 beta L. If you change the theta to this one, okay, the theory can connect to each other. We derive this equation by using this equation, right? The first equation comes from here, and the second equation, is from the circle. We use the gamma circle, the polar form, right? And actually it looks like each other, and that is why we define theta equals to -2 beta L. Okay? This is why. So for a circle is half wavelength. It's not the full wavelength, okay? A circle is half. It's very confusing. Theta here is not the electrical length. No, it is not beta L. It is -2 beta L on Smith chart. This theta is the theta on Smith chart. It is not the electrical length. This is very, very important because they use the same notation. You will be confused. There is a -2, right? They are different, but in POSA, I see the same theta. You will confused. But it is not theta. It's -2 theta. Okay? Okay. I think I detailedly show you how to talk about Smith chart, and maybe you don't need to remember all the details about derivation, but it's helpful to understand how to use it. Okay? So here is one of the example. Maybe you can use your Smith chart to follow what to do, okay? Use your Smith chart to find out if there is a load impedance which is 40 plus J 70. And you have the transmission line connected to this load, which has the characteristic impedance 100 ohm. Find out your first location at L equals to 0 on your Smith chart. Find out what is this point. Can you find the point? Smith chart, I definitely will. I will ask you in your final. Definitely, it's too important, and it's very worthy to understand. You have a Smith chart. Find out your here. Do anyone need a new Smith chart? Okay. Find out. This is a step. The first step, find this point. Okay, and if my length of the transmission line is 0.3 lambda, you change this line to 0.3 lambda, and you use your compass to draw a circle and find out the normalized real and imaginary part. Then multiply back to your Z0 and find out what is the answer. Try it. Use your compass. And I will see your answer if they are the same, okay? Don't pretend you understand but not. Don't pretend you should understand. I will change the number. It's very easy to change the number. You should know how to do this problem. Definitely will show in your final exam. And this is, you must get right. Okay. Find this. And you need to be guaranteed to know how to do here, and this is 0.3 lambda to get the reflection coefficient and also the input impedance at the end. And I think this is in your textbook, right? Oza, the same example 200. Okay, let's do exercise. Okay, if you show me the answer, you know how to do that, then it's done. You done? What's the answer? I want to number. What is the Z in? There's number, right? Multiply, and also you find out the reflection coefficient. Find out Z equals. There is find out the RL and the XL first, and multiply your Z0 to get back your Z. And what is the answer?会这样一个自我反思的能力的，所以我在就是在示范这一点。
它有很多这个都跟这个它就是它的答案这样子，它比例是相同，所以它可能会起很多抽到它的机会被标准化，就是说把这样说这样标准化在画里面，假设这些所有的关系到这个，首先它就是差的。然后它新的，然后它新的这个
You can stop, right?